So for day 3 of chapter 11, we are going to continue to talk about matrices. For day 2, we talked about using matrices to solve systems of equations using row operations. And today we're going to talk about a few other operations and properties of matrices. So first, in order for matrices to be considered equal, they have to be the same size, and every entry in the matrix has to be the same as the corresponding entry in the other matrix, meaning whatever entries in row 1, column 1 needs to be exactly the same entry as the row 1, column 1 of our second matrix, and so on, in order for them to be equal to each other. To add or subtract matrices, one, they have to be the same size, and then once the two matrices, we see that they're the same size, to add or subtract them, you would just add or subtract the corresponding entries between matrices, meaning row 1, column 1 plus row 1, column 1 in the second matrix gives you the entry in row 1, column 1 of your answer matrix or your resulting matrix. To multiply a matrix by a scalar, we would take a matrix of any size, really, and multiply every entry in that matrix by that scalar. So there is a property of scalar multiplication that we should talk about, and really the property is what we call the commutative property. So if I have these two equations here under the properties of scalar multiplication, do want to point out that m in these equations is a matrix, and c and k are real numbers or scalar numbers. So take a look at the first equation. If I have c multiplied by km, where k is a scalar, I could also do c times k first, multiply the two scalars or real numbers together, and then multiply that by the matrix. So that's one way to handle that, or one property of scalar multiplication. The other one is, if you look in the second equation, we're considering n to be a matrix as well. So if I am adding m and n together and then scaling it by the number c, what I could actually do is take m and multiply by c, and then take n and multiply by c, and then add those two matrices together, provided that m and n are the same size. Also, a zero matrix is kind of just like it sounds, a matrix where all entries are zero. And what it means is, in operations, it is the additive identity for all matrices of the same size. So what that really means is if I have a matrix A and I add the zero matrix of the same size, I would still get A. So adding a zero matrix to a matrix doesn't change it, which is what it means to be an identity. In matrices, we also have what we call row vectors and row columns. So a row vector is a matrix that is one row. A column vector is a matrix that has one column. Row vectors and column vectors for matrices definitely have some advantages and properties as we get into this chapter a little bit more, but just want to define those today because we will be using them a little bit down the road. And then matrix multiplication. What that means is taking two matrices and multiplying them together. And it is not how you would do addition or subtraction. You wouldn't just multiply the entry in row 1, column 1 times the entry in row 1, column 1 and get a number. It's actually a little bit more involved than that. So this paragraph here kind of explains that. First thing I do want to make sure is, can matrix multiplication be done here? So the first thing to check is that the number of rows in the second matrix is the same as the number of columns in the first matrix. If that is not true, then you can't multiply them. And then once you identify that these are two matrices that can be multiplied, you take each entry in row 1 in the first matrix multiplied by each entry in column 1 of the second matrix and add them together. That might not make a ton of sense right now. Putting it into words is maybe helpful as a reference, but the best way to see how to multiply two matrices is to see it in action, which we're going to do here in a second. But one thing I do is want to kind of draw out an example here. So let's say I have a 2 by 3 matrix and I want to multiply it by a 3 by 2 matrix. The first thing I should check is that the number of columns in the first matrix is the same as the number of rows in the second matrix. So if you look here, having them next to each other is kind of nice in terms of their size. The number of columns and rows in the first and second matrix is the same, which means I can multiply them. And then to figure out what size your resulting matrix is going to be, there's actually a kind of quick way to do that. And if you look at this 2 by 3 times 3 by 2 here, the number of rows in the first matrix and the number of columns in the second matrix will give you your size of your resulting matrix. So my resulting matrix when the multiplication is done, in this case, would actually be a 2 by 2. And you'll see how that works out here when we do an example. So for the examples we're going to look at, we're just going to identify a few different matrices. So the matrices A, B, C, D, and E are defined this way, and we want to just perform these operations we talked about: adding, subtracting, multiplying. So first example, we want to take matrix A and add it to matrix B. So what I'm going to do is write them. So matrix A added to matrix B. First thing I should check is that they are the same size. So for addition and subtraction, the two matrices need to be the same size. Both matrices are 2 by 2, which means I can add them, so I would add the corresponding entries. So for my answer, the first entry would be 3, so row 1, column 1 would be 2 plus 1 is 3, and then 2, and then 2 in the first entry in row 2, and 4. So to get there, I just added each corresponding entry in the matrix to the other, and I have my answer there. So matrix addition or subtraction, matrices have to be the same size, and you would just add the corresponding entries to each other. So for example 2, we want to take matrix A and multiply by matrix B. So before I can do that, or before I do that, I'm going to check to make sure that this multiplication is defined. So if you take a look, is the number of columns in row or matrix 1, which is 2, the same as the number of rows in the second matrix, which is 2, and the answer is yes. So the size of the matrix I'm going to get in this case is actually going to be a 2 by 2. So here's how the multiplication would work out. So I would take the first entry in row 1, which is a 2, and multiply it by the first entry in column 1 in the second matrix, which is 1. And I'm going to add that to 3, which is the second entry in row 1, times the 3, which is the second entry in column 1 in the first matrix, and that will give me my first entry. So it's row 1 times column 1, but you would add your multiplication together. So for my second entry of row 1, I would take the first row of matrix 1 multiplied by the second column of the second matrix, and that's where I would get that entry. So I'd get 2 times 1 plus 3 times 0. Sorry, 2 times negative 1 plus 3 times 0. That would make my second entry in row 1. And then for my second row in my answer matrix, I would take row 2 times column 1, and I would add the entries together, and then I would take, for the last entry, I would take row 2 multiplied by column 2 in the second matrix. So here's what I would get. Negative 1 times 1 plus 4 times 3, and that is negative 1 times 1, which is row 2 times column 1, plus 4 times 3, which is in row 2, column 1. And then for my last entry, like I said, I would take negative 1 times negative 1 plus 4 times 0. All I would need to do to finish this is just find out what those entries are. So 2 times 1 plus 3 times 3 would give me 2 plus 9, which is 11. That's my first entry. And then 2 times negative 1 plus 3 times 0 would be negative 2, but I'm going to do the second row first. Doesn't matter the order in which you write these down. So negative 1 times 1 plus 4 times 3 is also 11, so that's the first entry in row 2. Like I said, the second entry in row 1 would be 2 times negative 1 plus 3 times 0, which is negative 2. And then the last entry would be negative 1 times negative 1 plus 4 times 0, which is 1. So that is my answer for A times B. Again, the way you're going to multiply, you got to be careful here, is the first row times the first column gives me my first entry. The first row times my second column gives me my second entry in row 1. And then I do the same process through all the rows and all the columns of my two matrices. And that would be your answer. And for the third example, we are going to take 3, which is a scalar, multiplied by matrix D, and then add it to matrix E. So first thing I'm going to write is 3 times the matrix D, so I'd write what that matrix is, and add it to row E. So then I want to check to see if this addition will be defined. So if I look at this, I have a 2 by 3 matrix, D, and if I multiply that by a scalar, it doesn't change the size of that matrix. And then I want to add that to a 3 by 2 matrix for E, And because those two matrices are not the same size, then this addition is actually not defined. So you can't perform this operation. So the answer would be undefined, and the reason would be, since D and E are not the same size, I cannot perform addition or subtraction. And that would be it. So before you try and, maybe scale that matrix D, check to see what operation we're trying to perform. We're trying to perform addition, and addition or subtraction are only defined when the matrices are the same size. Now, multiplication in this case would be actually different. So multiplication could be performed because matrix D has 3 columns and matrix E has 3 rows, so I could actually perform this if it were multiplication, but because it's addition, I can't perform this operation. So for example 4, we want to perform some addition, so I want to take A plus the quantity B plus C, so I'm going to take matrix A and add it to the quantity of B plus C. See what happens here. So first thing, maybe I should write down what these matrices are. So there's matrix A, and I'm going to add it to B plus C. So I'm going to perform the operation just like I would order operations. So I'm going to add the two matrices in the parentheses, B and C, and then I'm going to add matrix A. So if I added B plus C, so I'm going to rewrite matrix A first, and then if I added B plus C, I would get 1 plus 1 for my first entry. Just you add the corresponding entries, and you'd get your answer for the addition inside the parentheses. So I'd get 2, and then negative 1, and then 3, 1 in row 2. And then if I want to add those two matrices together, obviously they need to be the same size. They're both 2 by 2, so just add entry-wise. So 2 plus 2 is 4, 3 plus negative 1 is 2, negative 1 plus 3 is 2, and 4 plus 1 is 5. So performing that operation, this was defined because all 3 matrices were 2 by 2s, so I could add them all together. For example 5, we want to perform D times C, which would be multiplication there. So I'm going to write the two matrices first. So D is a 2 by 3 and C is a 2 by 2. So we have to check to see if this multiplication is defined. So I have a 2 by 3 and I want to multiply by a 2 by 2. So what I have to check is the number of columns in the first matrix the same as the number of rows in the second matrix? And they are not, so actually this operation cannot be performed. And because of the way matrix multiplication is defined, if you tried to multiply it out, if you tried to take the entries in row 1 for matrix D and multiply by the entries in column 1, you'd see that you're short there. You can't actually perform that. So the quick check, obviously, before you start trying to go through and multiply would be see if it's possible depending on their size. And in this case, the operation is not defined because matrix D does not have the same number of columns as C has rows. So those numbers are different. And the last example we're going to perform here is we're going to take matrix A and multiply it by the square of matrix A. So what this really is matrix A times matrix A squared. So in terms of how to approach this, I would first square matrix A, follow order operations. So take care of that squared first and then multiply the matrices together. So I'm going to kind of rewrite this as matrix A times matrix A squared. So inside the parentheses, what I have to check is this operation defined, meaning is the number of columns in the first matrix equal to the number of rows in the second matrix? It is. So we have 2 by 2, 2 by 2, so there's no issue there. So if I were to perform this operation, I'm going to leave that first matrix A alone, and then I'm going to multiply the two matrices inside the parentheses. So I'd take the first row times the first column, and I would add them together. So it'd be 2 times 2 plus 3 times negative 1. That gives me my first entry. And then for my second entry in row 1, it'd be 2 times 3, which is the first entry of row 1 times the first entry in column 2. So 2 times 3 plus 3 times 4. So again, we're taking the first row of the first matrix multiplied by the first column to get our first entry, the first row of the matrix multiplied by our second column to get our second entry, and then I'll do the same thing in row 2. So I'll take row 2 and multiply by column 1, and take row 2 and multiply by column 2, and that's where those numbers come from. Now all I need to do is complete the arithmetic in there, so I would get that first matrix I'm going to leave alone, 2, 3, negative 1, 4, and what I would get is 1, 18, negative 6, 13. So 2 times 2 plus 3 times negative 1 gives me 1. 2 times 3 plus 3 times 4 gives me 18. And negative 6, 13. And now I want to multiply these two matrices together. Again, they're both 2 by 2, so the operation is defined. So what I would get is 2 times 1 plus 3 times negative 6 in my first entry, so that's row 1 times column 1 with the entries added together. And then I'd get row 1 times column 2, so 2 times 18 plus 3 times 13. That gives me my second entry in row 1. And then row 2 times column 1 in my first and second matrix give me negative 1 times 1 plus 4 times negative 6. And then row 2 times column 2 would give me negative 1 times 18 plus 4 times 13. So all I would need to do to finish this is just find out what these entries are. So the first entry should be negative 16, and then 75, negative 25, 34. So this problem obviously was a little more involved. I had to square a matrix, multiply it by itself, and then multiply it by itself again. And what I should get is negative 16, 75, negative 25, 34. So those are the operations that we're going to talk about today. As we get further into this chapter, there'll be some other things about matrices we need to be able to do, but matrix multiplication is really the one here that is going to be a little bit trickier, so just pay attention to your signs and your corresponding entries to make sure you don't make any silly arithmetic mistakes.